Normally I would take the examples and jump into the Shplait implementation of unify, but let's consider it again, all the possible cases just from a kind of pseudocode perspective. Suppose unify gets a type variable t and some arbitrary type tal2. Okay, so this is only one possible case of unify. The first argument is not always a type variable, but suppose it is a type variable without making any assumptions about tal2 yet. If t is set to some other type tal1, then we already know that t is equivalent to tal1. We can recur with unify on tal1 and tal2. Okay, so now we suppose that t is not set to something already. Another possibility is that we already know that tal2 is equivalent to the type t. Maybe because tal2 is literally t, and so we're trying to unify t with t. That should just succeed. But another possibility is that tal2 is some other type variable t3. Maybe t3 has an equivalence to t, and well, you can see how this keeps going. We can have these chains of type variables. Fortunately, we have the resolve function, so that is solving this problem of deciding is tal2, as when we simplify it as much as possible, is that already equal to t? Notice that, remember, t is not set to anything, so if we get to t, there's no further simplifications. So that's why this call to resolve is enough. All right, so this is the case when tal2 is exactly equal to t after all the simplifications that are possible, then we just succeed. There's nothing more to do in unify. It's also possible that tal2 is not equivalent to t, but it does have a t inside. So this is, say, when we're trying to unify t with t arrow t. And that's where our occurs check comes in. So if occurs detects that t is somewhere inside of tal2, we should just fail. We should not try to install any equivalence because it will create this kind of cyclic type that we would have to unwind forever. In occurs, we will handle the chains of equivalences, but it's also harmless if we want to resolve tal2 first to simplify tal2 as much as possible before doing the occurs check. Meanwhile, if none of these other cases happen, that means that t is unconstrained, tal2 is not already t and doesn't refer to t in any way, and so that means it can succeed. But that was just one of the possibilities for unify, where we assume that the first argument is a type variable. What about other possibilities here? So let's consider the more general case. We've got a tal1 and a tal2. Right? So tal1 is not necessarily a type variable. Well, tal2 might be a type variable now. If it is, then we can handle that simply by reversing them, because we can reverse the arguments to unify. It's implementing an equivalence, and then that takes care of that possibility. Okay, so it must be that tal1 and tal2 are not immediately type variables. In fact, they might both be int or boolean. In that case, we can succeed. Or they might both be arrows. And if they are both arrow types, then we've got argument types and result types here. And we recur with both of those pairs. So we take the argument type of t1 and the argument type of t2, see if those can be unified, and do the same with the results. And if both of these unifications succeed, then we're all okay. Now there are still many other possibilities, like maybe tal1 is a boolean and tal2 is an arrow type. But in all those other possibilities, we have some sort of mismatch and we fail. So it turns out that these are all the cases for unify, and you can see it's not just a simple recursion over the structure of our types. We have to really consider all the different kinds of interactions between these two arguments.